Yeah. Today, we shall study about electron orbits in atoms. The Rutherford nuclear model of the atom, which involves classical concept pictures of the atom, pictures the atom as an electrically neutral sphere consisting of a very small, massive and positively charged nucleus at the center, surrounded by the revolving electrons in their respective dynamically stable orbits. The electrostatic force of attraction, Fe, between revolving electrons and the nucleus provides the requisite centripetal force F to keep them in their orbits. Thus, for dynamically stable orbits in a hydrogen atom, Fe बराबर Fc. So, mb square by r बराबर 1 बटा 4 pi epsilon naught e square by r. Thus, the relation between the orbit radius and the electron velocity is r बराबर e square बटा 4 pi epsilon naught mr square. The kinetic energy K and the electrostatic potential energy U of the electron in the hydrogen atom are by 2 mb square बराबर e square बराबर 8 pi epsilon naught r and U बराबर minus e square बटा 4 pi epsilon naught r. The negative sign in U signifies that the electrostatic force is in the r direction, minus r direction. Thus, the total energy E of the electron in a hydrogen atom is E बराबर K plus U बराबर E square बटा 8 pi epsilon naught r minus E square बटा 4 pi epsilon naught r बराबर minus E square बटा 8 pi epsilon naught r. The total energy of the electron is negative. This implies the effect that the electron is bound to the nucleus. If E were positive, an electron will not follow a closed orbit around the nucleus. Atomic spectra. Each element has a characteristic spectrum of radiation which it emitted when an atomic gas vapor is excited at low pressure, usually by passing an electric current through it. The emitted radiation has a spectrum which contains certain specific wavelength only. A spectrum of this kind is termed as emission line spectrum, and it consists of bright lines on a dark background. The spectrum emitted by atomic hydrogen is shown in figure 1. A study of emission line spectra of a material can therefore serve as a type of print for identification of the gas. When white light passes through a gas and we analyze the transmitted light using a spectrometer, we find some dark lines in the spectrum. These dark lines correspond precisely to these wavelengths which were found in the emission line spectrum of the gas. This is called the absorption spectrum of the material of the gas. Spectral lines. Hydrogen is the simplest atom and so has the simplest spectrum. In the absorbed spectrum, however, at first sight, there does not seem to be any resemblance of order or regularity in a spatial and spectral lines, but the spacing between lines within certain sets of the hydrogen spectrum decreases in a regular way in figure 1. Each of these sets is called a spectral series. In 1885, the first such series was observed by a Swedish school teacher, John Jacob Balmer, in the visible region of the hydrogen spectrum. This series is called Balmer series in figure 2. The line with the longest wavelength 656.3 nanometer in the red is called H alpha. The next line with wavelength 486.1 nanometer in the blue green is called H beta. The third line 434.1 nanometer in the violet is called H gamma, and so on. As the wavelength decreases, the lines appear closer together and are weaker in intensity. Balmer found a simple empirical formula for the observed wavelengths. 1 by lambda over r, 1 by 2 square minus 1 by n square, where lambda is the wavelength, r is a constant called the Rydberg constant, and n may have an integral value of 3, 4, 5, etc. The value of r is 1.097 10 to the power 7 meter minus 1. This equation is also called Balmer formula. Taking n barabar 3 in equation 1, one obtains the wavelength of the line. 1 by lambda barabar 1.097 10 to the power 7, 1 by 2 square minus 1 by 3 square meter minus 1 by 1.522 10 to the power 6 meter minus 1. It means lambda barabar 6.3 nanometer. For n barabar 4, one obtains the wavelength of H beta line etc. For n barabar infinity, one obtains the limit at alpha barabar 364, lambda barabar 364.6 nanometer. This is the shortest wavelength in the Balmer series. Beyond this limit, no further distinct lines appear. Instead, only a faint continuous spectrum is seen. Other series of spectra for hydrogen were subsequently discovered. These are known after their discoveries as Lemons, Paschen, Brackett, and Pfeffer series. These are represented by the formula. Now, the Balmer formula may be written in the terms of frequency of light, C barabar L lambda, or 1 by lambda barabar nu by C. So, nu barabar RC 1 by 2 is common 1 by n square. There are only a few elements, hydrogen singly ionized, helium and doubly ionized lithium, whose spectra can be represented by sample formula. However, these results are empirical and do not give any reasoning why only certain frequencies are observed in the hydrogen spectrum. Bohr model of the hydrogen atom. The model of the atom proposed by Rutherford assumes that the atom consisting of a central nucleus and evolving electron is stable, much like Sun planet system which the model imitates. However, there are some fundamental differences between the two situations. While the planetary system is held by the gravitational force, the nucleus electron system being charged objects interact by Coulomb's law of force. We know that an object which moves in a circle is being constantly accelerated, the acceleration being centripetal in nature. According to classical electromagnetic theory, an accelerating charged particle emits radiation in the form of electromagnetic waves. The energy of an accelerating electron should continuously decrease. The electron would spiral inward and eventually fall into the nucleus, as shown in figure 1. Thus, such an atom cannot be stable. Further, according to the classical electromagnetic theory, the frequency of electromagnetic waves emitted by the evolving electrons is equal to the frequency of the revolution. As the electrons spiral inwards, their angular velocities and hence their frequencies would change continuously. And so will the frequency of light emitted. Thus, they would emit a continuous spectrum. In contradiction to the line spectrum actually observed clearly. Rutherford model falls only a part of the story, implying that the classical ideas are not sufficient to explain the atomic structure as shown. An accelerated atomic electron is shown in figure.